Hello, my name is Pracheth and welcome to my channel. So in this video, I'm going to talk about timers in this 8-bit microcontroller by Nuvoton W78E052D. My aim is to give you a practical insight on how timers work at register level. So there are three timers in this microcontroller: timer 0, timer 1 and timer 2. So as it's a 8052 based microcontroller, there is this additional timer 2 which has this amazing feature of capture and up-down counting, which we'll see later. But for now, let's take a look at timer 0 and timer 1, which is common with the 8051 microcontroller. So there are two registers which they share in common, tmod and tcon. So the tcon is bit addressable, so we can set this individual flags, okay, and clear the individual bits. TR is timer 1 run control bit, TR0 is timer 0 run control, TF1 is the flag for timer 1 and TF0 is the flag for timer 0. So in this tmod register, there are this low 0 to 3 bits which are used for timer 0. To select timer 0 or timer 1, we use this tmod register. So these all bits are for timer 0 and these all bits are for timer 1. So M1 and M0 are used to select the mode. So both of these timers, timer 1 and timer 0, are both 16-bit timers. They have their own counting registers, TL0 and TH0 for timer 0, TL1, TH1 for timer 1. So 8 plus 8, 16. Because it's a 8-bit microcontroller, it has to use two registers to make 16 bits. To select the mode, we are using these two bits, M1 and M0. So if we use 0, 0, then timer 0 is selected in mode 0. If here we use 0, 0, and timer 1 is selected in mode 0. So both of these timers 0 and 1 has 4 modes, 0, 1, 2 and 3. We are going to see step by step. First we will see timer 0 in mode 0. So when M1, M0 is 0, 0, it's mode 0. It's 0, 1, mode 1, 1, 0, mode 2, 1, 1, mode 3. So this diagram will make you more clear that how we should set the registers, okay? So tmod, in this tmod, the gate has to be 0. Then only here it will see 1 and this output will be 1 of the OR gate. Okay, and then only this run TR0 or TR1 bit, when we will set, the timer will start to run because this output will go high and then only it will pass the counts. So the C comma T bar value, if it's 0, then it will count the oscillator frequency divided by 12. So 16 megahertz divided by 12 is 1.33 megahertz, which will be counted by this counting registers. So if it's 0, then timer is selected. If it's 1, then we are counting the external pulses from the external pin, 3.4 or 3.5, depending on the timer we have selected. If you have set this bit, which is for timer 0, then we'll use 3.4, okay, to give the pulses to the counter. So the counter will increment. If you have selected mode 0, that means when these two bits are 0, then so let's set the tmod value for timer 0 in mode 0. We can also use timer 1 in mode 0, but I'll be using timer 0 to explain all the modes. So this gate must be 0, C comma T bar is 1 because we want to use external pulses to see what happens. This is mode 0, so that's why M1, M0, 0, 0. This all bits will be 0. So if this all bits are 0, the question is asked that will this timer 1 is set in mode 0? And the answer is yes. So this timer 1 is also set in mode 0, but we are not running the timer, okay? We are not setting its flag. We are only running timer 0. So this value in tmod will be 0x04. Okay, then we will use this TR0 flag to run the timer. So here I have created a new project for W78E052D in Keel IDE, and this is the header file for this microcontroller. So you have to include this header file. If you open this document, it contains all the special function register specific to this microcontroller. So now let's write a code for timer 1. Now let's program timer 0 in mode 0, which is a 13-bit timer. Let's compile this and debug. So we don't need to upload this code in the microcontroller. We can just see the status on this debug peripherals. So we'll be using pin 3.4, which is our T0 pin, to increment the counter. Timer 0. Now we will run this code, and as soon as I run this code, you will see that 13-bit timer counter. So this is the mode which is selected, 13-bit timer counter, because in mode 0 the timer acts as a 13-bit. So 13-bit means TL0, only 5 bits of TL0 are used and 8 bits of TH0 are used. So TL0 will go on all the way to, so 2 raised to 5 is 32. So if we convert 32 into hex, you will get 20. Okay, so that is the value when the overflow will happen. But if you will see 31, then it's 1F. 1F for F means all the 4 bits are 1, and then 1 is for the last bit, which is the 5th bit. So it will go all the way to 1F, and then on the 32 count, this TH0 will increment. You want to see? I've run the code. This is the 4th bit. We'll toggle. And again I will give falling edge on pin 3.4. It's incremented to 2, 3, 4, 5, 6. And I will go all the way to 1A, 1B, 1C, 1D. So now it's 1E, 1F. And after this, after 1F, the overflow will happen. Okay, you can see on the falling edge, TH0 was incremented. 32 counts, after 32 counts, TH0 is incremented. So this means that TH0 is FF. It will go all the way to FF. So if you will see, 255 will give you FF. But 2 raised to 8 is 256. So after FF, on the 256th count, the flag will set. Okay. So what I will do now is, and here I will load TL0 with 0x1f and TH0 with 0xff. So this is the last count. Okay, that means we are utilizing the full, all the 13 bits you have made 1. So 2 raised to 13 gives me 8192. So on 8192, the overflow will happen. If I convert 8191 to hex, we'll see 1FFF. So 1F is nothing but TL0 and FF is nothing but TH0. So in this way we come to know that the first two values, 1F is stored in TL0 and FF is the last two are stored in TH0. Okay, so all the bits are filled now, means all the bits are 1, and after that we give 1 count, the flag will set. And bit to bit 3.4 we will give 1 and the flag is set. So TF0 is set now and it will remain set. Okay, it will not get clear, so we have to manually clear it. So what will happen if we will run this timer with the 16 MHz divided by 12 clock pulse? The question is, after how much time the flag will be set? So that means for 8192, how much time will it take for the overflow to happen? So the clock frequency is 16 megahertz. 16 megahertz divided by 12 gives you 1.33 megahertz. 1 divided by frequency will give us time. So we will do 1 divided by 1.33. So that's 0.750 microseconds. So 0.750 microseconds is the time for one clock pulse. And like this, how many clock pulses will set up the flag? 8192. So 8192 into 0.750. So it will take 6.144 milliseconds. 6.144 milliseconds. So after 6.1 milliseconds, the flag will set. So let's toggle output pin when the flag is set, and then we'll clear the flag. So we will not load this because we want it to be 0. After the flag is set, we will declare a LED pin. And this is a S-bit variable. And after the flag is set, we will wait till TF0. So we will wait here. Now we don't want the external clock pulses to trigger, so T mod will become 0x00 because now C, T bar bit is cleared, so that value is 0. So T mod is 0x00. We will run the timer 0. We will wait here because the flag is 0 now, so it will be stuck in this while part. So after the flag sets, it will jump to the next line, and now we want the flag to be cleared, which was a set flag, okay, that we will clear now. And after the flag is cleared, we'll toggle the LED. So I think this must be capital P. Now let's build this. Yes, 0 error, 0 warning. So now I'm going to show you how to view waveform in this Keel IDE. So you click on this analyze window, go to setup, you click on this window and write the variable name that you want to see the waveform for. Okay. Yes, the color also you have to select. I'll keep it red. Maximum is 0.1, minimum is 0, 0x0. Okay. Now we'll run this. You can see that the waveform is getting generated. So if I will stop this and measure the time, I will click on this cursor. And 6.11, you can see the D value here, the difference 6.177 milliseconds. And that was actually the calculated value, right? 6.1 milliseconds. And that was T on, and T off is also, T off must be also equal to 6.14 milliseconds. So 6.11 is the maximum delay that we can generate using this timer. So if you want to generate a square wave which is greater than 6.11 millisecond T on and T off, so what to do? Yes, the answer is that we need to generate a delay like Arduino. So let's do that. So we can generate a base delay of 1 millisecond and then run a for loop depending on the variable passed. So just like Arduino, we will make a delay function. Okay. So we will cut this and write here void delay. So this delay function will take unsigned in t, and we want to generate a base delay of 1 milliseconds. So similar to how we calculated time, so we multiplied the time 0.750 microseconds by the counts 2 raised to 13, which was a 13-bit timer. So 8192 into 0.750 microseconds gave us 6.1 milliseconds, which was the time duration. So from the counts we can get time, and from the time we can get count, right? So if we divide 1 millisecond by 0.750 microseconds, then we get 1.33. So multiply this by 10 raised to 3. So 1333.3. That is that many counts we need, okay, for 1 milliseconds. So that much counts needs to be passed for the flag to set. So we want the flag to set after 1333 counts. So we will write 8192. We know that on 8192 count the flag sets. So we'll subtract this count value by 1333.6859. So this value we have to load in the TH and TL. So we will convert this into hex. We'll copy this, and the hex value is 1ACB, and you know 1A is TL0 and CB is TH0. So when we will wait here, this will generate a base delay of 1 millisecond. So when we will go here, actually the flag sets, that means this both values are now 0, okay, because the flag sets when the roll off occurs from FF to 00. So we have to load that again. So we have to put this in for loop, which will go from here. We have to declare a variable int I for the for loop. I is equal to 0. I is less than t I plus plus. So the loading, starting the timer, waiting, clearing the flags will happen every time for the t times. So we will wait here for 1 milliseconds for this much amount of time. So the value will pass here. Suppose if it was 2, then you will get a delay of 2 milliseconds. But notice this is 2 milliseconds. Waiting here is 2 milliseconds. But this loading of registers also take machine cycles. Okay, so this time we are not calculating. We are neglecting this, and this error will add on. But that's because the auto reload function is not available here. So you have to load it from the software, and that's straining the ALU. But if there was auto reload feature, we would have not wasted the machine cycles here, and we would have kept running the timer. There will be only while loop in the system. We will generate that delay when we will see timer 0 in auto reload. So for now, let's see whether this works or not. So we'll generate a delay of 3 milliseconds. Okay, 0 warning. Now let's go to debug and run this code. This is our square wave. I will stop this and I will see T on whether we are getting 3 point. So yes, 3.8 milliseconds we are getting here, T on, and T off is also 3.8 milliseconds. So you can see it's not that accurate. It's generating a offset of nearly 0.8 milliseconds. So what if you want to generate accurate delay? And the answer is to use auto reload. So in this way we can generate delay using timer 0 in mode 0, and similarly if you will use timer 0 in mode 1, then the counts will change from 8192, because as we are using 16, all the 16 bits, the count will be 65536, that's 2 raised to 16. Okay, so on 65536 the flag will be set, so that means 65535 all the bits will be 1. Okay, so if we will convert 65535 to hex, you will get FFFF, that means FF for TL0 and FF for TH0. So your aim is to just generate a delay, and the maximum delay will be of 49 milliseconds. Yes, the maximum count is in 16-bit mode, the maximum count is 65536. If we multiply that with 0.750 microseconds, that will give us 49.1 milliseconds. So let's use that. Let's toggle the LED just to show you. So what we will do, put tmod in 0x001. This is timer 0 in mode 1. So the LED will toggle every time the flag is set after 65536 counts. Okay. So now TF0, we will wait here and clear the flag, then toggle the LED. So we are running the timer in mode 1, timer 0 in mode 1. We'll start the program. So if we'll see T on, yes, it's 49.4 milliseconds. Yes, 49.5. So in this way, you can see that the maximum delay that we can give is 49.1 in timer 0 mode 1. That's just because the counts are more in timer in mode 1. But what if the delay is 100 milliseconds? So we have to use this for loop and this loading by the software. It takes the machine cycles. Every time we run the for loop, it adds error in the delay. So let's use timer in auto reload mode. So let's go to the diagram and understand how that works. Let's configure the tmod register for timer 0 in mode 2. So M1, M0 will be 10. Just all the bits will be 0. So if we are using it as a timer to count the oscillator frequency divided by 12, then we'll keep this 0. But let's keep it 1, okay, because we want to see how the registers increment and the flag sets on the beat of the external clock pulse. So we'll keep this 1, so the value in the tmod register will be 0x06. So this is 6, okay. And suppose we want to use it as a timer, then we'll make this 0, then the value is 0x02. So this is a logic diagram of timer 0 in mode 2. In mode 2 it acts as a 8-bit auto reload. So every time the timer overflows, 8-bit timer TL0 overflows, it will reload the values from TH0 again to TL0. The counting will start from that count. So this part remains same, right? Gate is 0. When you start the timer, it will count the external pulses. It will count the falling edges. And when the count reaches FF, okay, after it goes from FF to 00, it will trigger a buffer which will load the values, will set the flag, And now it will start counting from that value. Suppose it was 3, it will start counting from the next clock pulse. It will become 4, 5, 6, and it will go to all the way to 255, which is FF. And then when it will roll off from 255 to 0, it will set this flag. So it is set previously, right? So it will not set this flag, it will just load the contents again. So this flag needs to be cleared by the software, or we have to call the interrupt to clear the flag. So let's see how the flag is set and the value is loaded from TH0 to TL0 in the kill IDE. Let's program this and see how this works. So now let's write a code to put timer 0 in mode 2. So tmod is equal to 0x06 because we want the external clock pulses to trigger and increment the counter. So we want the third count to set the flag. So I'll load TL0 with 0xFD. So FF is 256. If we minus 3 from 256, then we get 253. If we convert it into hex, we will get FD. And that value we will load in TH0. So after 3 counts are passed, the flag is set and again FD is loaded into TL0. Then we will start the timer 0 and we'll stop here. So yes, this is the code, we'll run it. Let's debug it. So if we toggle pin 3.4 on the falling edge of pin 3.4, the TL value will be incremented. So I will run the code now and the mode is set to 8-bit auto reload. So right now if I give a falling edge on pin 3.4, TL0 is incremented to FE. Okay. Again if I give a falling edge, it is incremented to FF. Now on the next count, next falling edge, TL0 will set the flag and the values of TH0 are again loaded to TL0. Okay. And now on the next count, it will increment to FE, FF, and again FD. TH0 is again loaded into TL0, and from there the counting will go on upward. So this reloading takes place after FF. So it's very important feature, this auto reload. It can be used to generate delays. So we don't need to load the count again in the for loop. We just need a while loop and we have to count how many times the flag is set, and that will give us the delay. So this is how this works. I will stop the program. Stop the debug session. So if this was to be run as a timer, that means counting the oscillator frequency divided by 12, then let's see what will the time maximum delay that we can generate. So the maximum count possible is 256 times the time for one clock cycle, 0.750 microseconds. So it gives us 192 microseconds. So the maximum delay that we can give using timer 0 in auto reload mode is 192 microseconds. So we can generate a base delay of 100 microseconds. So let's calculate value for 100 microseconds. So 100 divided by 0.750 microseconds is equal to 133. So we need to pass 133 count to set the flag. So we'll subtract this 133 from 256. Okay. 256 minus 133. And that gives us 123, which we need to convert to hex. So it's 7B in hexadecimal. So let's load 7B here. So here in mode 2, we don't need to load the values again and again. Initially only we need to give all these values, and after we start the timer, we'll go into the while loop. For toggling the LED, we need to check whether the flag is set or not. So initially the flag is clear. So we'll check if TF0 is equal to 0 is equal to 1. If the flag is set, then we will toggle the LED, and initially we want the LED to be off. So we'll write LED is equal to 1. We'll put the timer in mode 2, and yes, now we are running it in the timer mode. So we'll write here 02. TL0 is 7B, TH0 is 7B. We'll start the timer, and it will be again loaded to 7B. It will count from there. So after starting the timer, we'll go in this while loop and we'll check whether the flag is set or not. If the flag is set, it will toggle the LED and will clear the flag. So in this way, we'll generate a square wave in auto reload mode. It will give a accurate delay because here we are not loading the values again. It's only one time. So yes, one more bracket for void main. Let's debug this. Now we'll run the program, and this is our square wave. So let's see whether we are getting 100 microseconds or not. So we'll stop this waveform. And yes, we are getting approximately 100 microseconds. Here you can see the delay D value is 99. Okay. So you can see the D value is 99.00 microseconds. That's very accurate. And T off is 0.110 milliseconds. That's 100 microseconds. 0.100. So it's 100.5 microseconds. So it's very accurate. So the time base of 100 microseconds, we can use this to generate a delay. So we can increment a counter here. We can write a count variable which will increment. And for that many counts, it will be stuck in the while loop. So while C is less than T, we'll write the function like this. So if T was 0, C has to be, so if T was 2, C has to be greater than 2. So 0, 1, so it will run 2 times, and once it becomes 2, it will be out of this while loop and we will stop the timer. So in this way, the while loop is stuck till that amount of time. So let's put this in the delay function. Delay auto-re is our function. We will declare a count variable to count how many times the flag is set. Initially, we'll keep it 0. So in this way, whatever T value we will pass multiplied by 100 microseconds will be the time delay. So if we'll pass 2, then 200 microseconds will be the delay. If we'll pass 10, so 10 into 100 will give us 1000 microseconds, which is 1 millisecond. So the formula for millisecond is into 10. So what if we'll write here T into 10? So this delay will be for 1 millisecond. So let's see whether when we will pass this 1 here, whether it generates a delay of 1 millisecond or not. Blink a LED with this delay auto-re. So initially LED we will keep 1. Initially we'll turn off the LED. Okay, 0 warning. So yes, we'll break from the while loop and then we'll stop the timer from running. So yes, so this was the bracket for while loop and this was for the if. So this is a square wave waveform. Let's see whether T on is 1 millisecond or not. So yes, it's precisely 1.0 milliseconds. So this is what I wanted. Accuracy of 1.0. So the next digit must be 0, 1.06 milliseconds. So if you are generating a delay of 1 millisecond, we don't want 1.2 or 1.1, we want 1.0. So here there is a consistency of delay in auto reload because we are not reloading it from the software side. So now I will generate a delay of 3 seconds and I will blink LED connected to the microcontroller pin 3.6. Okay, so we'll connect the LED to the microcontroller and upload it to the board. So yes, now we'll generate the hex file and upload this code to the microcontroller. So yes, the LED is blinking on the pin 3.6 with a delay of 3 seconds. So let's use a stopwatch to see whether the delay is accurate or not. Now let's see timer 0 in mode 3. So for mode 3, M1, M0 will be 1, 1. Just all the bits will be 0. So the value to be loaded in T mod will be 0x03. So that will put our timer 0 in mode 3. So in mode 3, it acts as a two individual timer counter. TL0 acts as a separate 8-bit timer counter and TH0 acts as a separate 8-bit timer counter. So TH0 doesn't act as a counter, it is forced to act as a timer as the oscillator frequency are directly fed to TH0. So TH0, when it will overflow, it will set TF1 flag, which is taking from timer 1. And also TR1, which is timer 1 run control, is now controlling TH0. So when TR1 will be 1, the clock frequency divided by 12 will be passed and this value will increment, okay, all the way to FF. And when the roll off occurs, the TF flag will be set. It will generate an interrupt. In similar way, TL0 acts as a normal timer, 8-bit timer with all the controls like TR0 gate and T0 can also act as a timer and counter. So in this way, it can be used in many applications. It can be used to generate baud rate because TF1 flag controls the baud rate in UART. So that is one of the application of timer 0 in mode 3. And also I have an idea of what if we set this flag to run this timer. So what if we cross couple? If this flag is set, we will set this to run this timer, and when this flag is set, we will set it to run this timer. So in this way we are cross coupling this. So it acts as a oscillator. So this will determine the T off of this and this will determine the T off of this. So there is a PWM signal generated on either of the flags. If you clear this flag and toggle a LED on this output, then a PWM signal will be generated. So if you understood the concept, you can use it in your own applications because we have this two timers now which can be used and it sets two flags. Now let's go to kill ID and see the PWM generator code. So this is the code for timer 0 in mode 3 and this generates PWM signal on pin 3.6. So X determines the T off value. Initially we turn off the LED. T mod is equal to 0x03. Then we load TH0 and start timer 1. We start TH0. Now TH0 started to counting from this value. Okay. So as in mode 3 both the timers are of 8-bit, we are restricted to give T on and T off of maximum 192 microseconds. So both of these addition must equal to 255. Okay. That is the maximum delay that we can give. Then we start the timer and we enter the while one. Now we have started the timer TH0 and we'll check whether TF1 flag flows or not. And if it flows, then we'll clear the flags related to TH0. We'll turn on the LED. That means if we put 0, we've connected LED in common anode. So that's why when LED is equal to 0, it will be turned on. But actually we are turning it off. We're turning off the pin. So we turn off the pin. We load TL0. We start the TL0. Then we check whether the flag sets or not for TL0. Once the flag sets for TL0, then we clear the flags related to TL0 timer and we turn off the LED, and then we load TH0, start the timer of TH0, and then we again check whether TF1 sets, and this repeats in loop. And in this way a PWM signal is generated depending on the value of X. So when X is equal to 1, we have a T off. It should be 0.750 microseconds. In this debugger we are getting 10 microseconds, so I will show you. So this is the PWM signal for X is equal to 1, and you can see the T off is, so yes, the T off, you can see it's 10 microseconds, 10.5 microseconds, and T on is 1.99 microseconds. So let's set X value to 255. So it's generating PWM signal with minimum T on. So in this way we can generate a PWM signal with varying T on and T off. We can control the brightness of the LED. So yes, this was the application of timer 0 in mode 3. I hope you enjoyed this video. This video covered timer 0 and timer 1 in all the modes. So timer 2 I will cover in the next video. So like and subscribe my channel. Share it with your friends. Thanks for watching.